So, hello. Good afternoon. Welcome to this session. How are you doing? Good. Yeah, thank you for your time. I know 5 p.m. is challenging, even for me. So with my jet lag, it still feels like 2 a.m. in the morning. So if I start singing here and dancing, then my body just changed to party mode. So if that happens, relax, everything is okay. So I'm Markus Großmann. I'm working for XL2. XL2 is a joint venture of premium automotive OEM Audi and Capgemini. And XL2 works on digital transformation projects for SAP S4, analytics, and also cloud. And together with my colleague Jens Busch, we put together some content for you on smart serverless architecture for smart manufacturing. I need to apologize for Jens. So he could not come to Las Vegas. He is definitely not dancing currently at the moment, but he's sending us his warm regards. We are both solution architects working in the domain of production logistics. And I'm located in Heilbronn. I have the pleasure there to work with a really cool team. And my second passion, besides architecture, is music. So I like to be creative. But today we will talk about not music, but software architecture. And it will be mostly about design principles and patterns. Experiences that Jens and I collated together from our work on smart manufacturing projects, especially with serverless technologies, and that it's not getting too theoretic and abstract. I'll also present you some solution examples for all those principles. Yeah, so smart manufacturing is a broad topic. Here are some pictures from our Audi plants. So if you ask somebody what is smart manufacturing, we'll probably get multiple results or multiple answers. So some will think of people wearing VR glasses or having tablets and checking the process results. Others will think of CAD designs with digital twins. Others will think of autonomous vehicles or logistics systems that brings the parts to the manufacturing belts. So smart manufacturing is a broad topic, and I can't promise that the principles and patterns we present will work for everything. What we have in mind and what is the focus is the layer above the shop floor. It means the systems and applications that control the shop floor layer or that get data from the shop floor layer. And as a real use case I brought to you today is a parameter service that we developed for Audi in the past years. So it is used to transmit car-specific settings and parameters to production line stations. So for example, you have a station that does calibration of rear axles or the positioning of headlights. So this is very specific for each car model. And therefore, all those stations need these settings that they work correctly. And in the past, this was done with USB drives, so people had to go to the machines and do it there. So this is really a cumbersome process. And what was developed here was a system that works in the cloud, is developed with serverless services, and provides a web application to manage all those parameters, and also takes the results from the manufacturing process to give analytics and to visualize any disturbances or outliers. And for connectivity to the shop floor layer, we used AWS IoT Greengrass. We will have a closer look on this example in our agenda. So first we'll look at architectural challenges. So for architects, the requirements are always important, and this will set the baseline. And we'll then deep dive into a series of principles and patterns. So we'll look at component-oriented design and service stores, elastic data models, the idea of closed feedback loops, and I will also have a look at development principles for serverless projects that we also experienced. And in the end, a summary, and I'll be there for Q&A, so if you have any questions or discussions, we can do it. First, challenges. Architects always need challenges, otherwise they would be unhappy. So, and fortunately, there are enough challenges for manufacturing systems. So production happens all around the globe in all times, so they have to be 24/7 available. They are always risk class 1, so they are closely dependent to production, and every minute is really a problem. And therefore, they need to be very stable, very robust, very resilient. So it means not only for disasters that do not happen so often, but also for the nitty-gritty errors that could happen, wrong data quality, interfaces not sending the right data. All this needs to be processed by these machines and that they do not have any outages. And if they would have, the RPO and RTO rates are so short that they need to get into production again very soon. Scalability, we've seen it in the last couple of years, going up, going down with the lockdowns or with the part shortages, or then the other way up if you have parts that you can produce more. And last but not least, security. Network is now as important as power on the shop floor. So, and when we've seen it more and more, that also those machines and the shop floor can be interesting for attackers, that they can do malfunctions there or attacks. The good thing is, if you look at serverless, it is generally a good architectural answer to this. Serverless technologies, so from AWS, are highly available, and scalability, this is everything built in. You typically have event-driven workloads in your production, and this is also very well supported. You have tons of services. Every reInvent produces new services that are ready to integrate on your fingertips. And yeah, also durability, error handling, this is already built in retry mechanisms. There's a lot of things that you can reuse here. Also security, there are built-in mechanisms you just have to configure and it's thought about. And with serverless, you also have less maintenance effort. And if production goes down in lockdown, you also have advantages with the pay-per-use model. So, check mark, everything solved. No challenges, unhappy architects? No. Fortunately, there are more challenges, especially for smart manufacturing. And actually, the principles and patterns I will present will focus mainly on those additional challenges. This is reusability. We don't want to implement things twice. We want to reuse, we want to standardize, and we want to be highly adaptable. So a lot changes in the automotive industry, in the processes, with the move to electric vehicles. The stations are changing continuously, and the systems have to adapt very quickly to this. And a key point, which we'll also have a look in more detail, is self-optimization. This will be a key factor in the future for managing all the complexity and be more resilient to disturbances. But before we look at reusability as a goal, I want to state a quote that I read from a copywriter, and he is saying, "We are not in the business of being original. We are in the business of reusing things that work." And I was really surprised to read this from a copywriter. I also always thought copywriting is a very creative profession. So have to reinvent or invent new things all the time. You have to invent new slogans. And he's saying the opposite, more or less. What does this mean for our profession as architects? I, as an architect, also want to try out new things. I'm interested in doing things and inventing solutions that were not possible some years ago. So, is it a bad thing to invent new things, to reinvent new solutions? Is to reinvent something bad? Well, no, of course not. But it comes with a risk. And the risk is adding complexity to a complex system will make it even more complex. So this sounds perfectly logical, but if you look at manufacturing systems, we are often a bit neglecting this truth. So we see manufacturing system in silos, so each plant could be a silo, and we see isolated solutions there. We see a lot of different solutions there, different machines. And what then happens is that solutions for the same problem are reinvented multiple times, and this increases the overall production system complexity. So it means if we invent new things that were not there before, this is good, but we should have in mind if we reinvent new things, those should be standardized or candidates to get standardized, and we should aim for reusable and mature solutions that could be reused. Why I'm telling you this? What does this have to do with serverless? So I took here an arbitrary screenshot from a blog post on serverless. Not sure if you recognize it. But what you can see is there's a lot in there. So there are lots of bells and whistles, a lot of elements in serverless. And the risk is, it is so easy to create dependencies there between all those elements. And this reminded me on OO technology. When object orientation was invented the first time, reusability was also a motivational factor. But some years later, was found out that object orientation was misused and created systems with a lot of dependencies that were difficult to maintain, and the term big ball of mud architecture or systems came along. And therefore, we need to take care, also with serverless, that dependencies do not kill us. And this brings us to our first design principle for reusability, which is component-oriented design. We see it as a prerequisite for having reusable solutions that you follow fundamental architectural principles. And this is component-oriented design and homogeneity. So component-oriented design, Edgar Dijkstra proposed separation of concerns in 1974. So this is really old, but it is still one of the strongest weapons that we have to manage complexity. So separation of concerns means that we separate technical code from business code, that we have patterns like model view controller, which do separation. We have layers, architecture with layers, this is separation. So we manage complexity by splitting the complexity in smaller parts. And component-oriented design also means design by contract. It means every component has interface, an outside view of the component that all the users of the component can see. And this hides the internal complexity of the components. So components also have an internal view. And this is all only relevant for the developers that are working with this component. Information hiding is also the need-to-know principle. It means all the details about a component is hidden inside the component, so the outside users do not need to know it. And they will also, in the APIs of the components, only get the information and the access they really need. And data sovereignty means that only the component is allowed to manage its data. So there should be no dependencies from other parts that grab into the data of the component. But ideally, also the data should be split up in components. And homogeneity, it means that you should solve similar problems in similar ways. For example, security. It's good to have microservices, and each microservice could have its own technology stack. This is fine, but if you are talking about security, you should check that the solutions you have are working for all the microservices. Another example would be monitoring and observability. So it can be really a problem if you have a system which has different ways of monitoring in each of the microservices. So some are using correlation IDs, some are using log files, some are using CloudWatch logs in JSON. So if this all is very different, and if you have a problem in your production system, and you get a call and you're telling this person, I need to analyze how to analyze the system, this is not so good. And therefore, for observability and monitoring, and also for security, it's very important also for serverless applications to have similar solutions for similar problems. So how to apply those principles to serverless applications? First step is that you group your resources that you have into microservices, or you could also say more abstract, into components. And cut them by using those principles of the component-oriented design. It means you could, for example, separate it by business concerns or business capabilities. And what we did at Audi, for example, was that we made a drill down of our concerns or business domains that we have in production and logistics. And we saw those are similar. Across the plants, they are similar. So we have order process, we have product identification, we have product positioning localization, we have task authorizations, process result collection, and so on and so on. So this is kind of the high-level domains that we have. If you go into each of those domains, you could also have a drill down of it. And this could help you to find the right boundaries for your components or your microservices. Second step, decouple those components or those microservices by using AWS Application Integration Services. There are a number of good and very easy to use services here like SNS, SQS, API Gateway, AppSync, EventBridge. They make it very easy to define the outside view of a component and the interface to it. And if you define those interfaces, do it very clear. Make it clear what is provided by this component, what is the API. And you could leverage here also specifications like Open API, also standards, or also async API, which is similar to Open API, but works, for example, for SNS, SQS interfaces to describe them. And then decouple dependencies to external systems. So if you have an MES system or shop floor stations, so the dependency to your shop floor layer, this should be decoupled with an own adapter or proxy component that you have. And this is more a general rule, apply well-known serverless design patterns like SNS, SQS, fan-out pattern. So let's take the example of our parameter service. This first step, this is a very simplified view of the architecture, but what you can see here is that we grouped our AWS resources in components, so in boxes. This is architecture, boxes and arrows. And they are grouped, and you may also see it is not only microservices that are grouped, but also an message event bus. This is also a component in this way. And each of those components have their own CI/CD pipeline, have their own CloudFormation stack, have their own development life cycle, and could be independently deployed. And then decouple those components with integration services. So for here example, this parameter offsets microservice has a REST API that it provides to the composite UI for the services that are called synchronously by the UI. But it also has an SNS SQS interface to the event bus to talk to other microservices. So there are no direct dependencies here. The microservices, when they communicate with each other, do not call the REST services. They work in a synchronous way, and this is also a very important pattern if you work with serverless applications. It is nearly always using events and an event-driven architecture. So if you have serverless and it makes sense, then go for an event-driven architecture. And the dependency to the shop floor is also decoupled with a component here, the station dispatcher. The station dispatcher just has the task to encapsulate the protocol that it speaks with the stations, which could be here UDP or MQTT or OPC UA or anything else. So there's not much business logic in it. It just decouples the communication protocol. So now we have our components. Then go to the next step. If we have components and we want to reuse them, there needs to be some repository to make them available. And what is a very popular repository that everybody of us uses and where we could learn how to share components? Let's look at app stores, how they do it. In App Store, you have an ecosystem of applications, and usually they solve a single use case and do this quite good. There could be also competing applications that do the same. Messenger applications, for example, so we have a lot of different solutions for this. And the dream of the business department for manufacturing would be to have something like this for their manufacturing plants, that they just click on an app store or marketplace or whatever, and then they have deployed this solution in their plant. It's not that easy. But you should, or what we also did was to create a service store. You may know AWS provides the service catalog concept, and with this you could deploy or configure standardized solutions. But this could be maybe too fixed, so not allowing a lot of customizations. And so this service store could also be an organizational thing that is not directly deployable. But the most important thing is it needs to provide the information about that there is a solution. That in Volkswagen and Audi, we have a lot of different brands. And somebody in Mexico should know that somebody in in Hungary has developed a solution that may be also fit his use case. And in order to have this information, we need this service store. And the service store should contain those business components or microservice bundles. And those components should be ready to use. That means if you are going and want to use this microservice bundle and customize it for your purpose, you should not have to do security compliance checks or open source checks or confirmation in any kind. Those should be really ready to use, that you do not have to do a lot of organizational stuff to really get it. Those components should also be well sized. That means whole applications to put here in the service store is maybe too big. Very little service that just gives you a stock value or a very tiny thing is maybe too small because the amount of effort to implement it by yourself is maybe lower than searching for such a small thing. So it should have a good size of some microservices, maybe 5 to 8. This is a good size. And it needs to be cost attractive. Why? Of course, nobody will use a solution if he does not know what costs are incurred by this. What does it mean to run those services? And if you have the service store, you could then also put it in an ecosystem that you have on the bottom layer, your AWS services, and on top of this, what a lot of companies have, a landing zone with shared technical platform services, like, for example, the shop floor connectivity could be such a shared technical service, or network connectivity between your plants. And so the service store would then sit on top, and all this would then help you to build your business applications. And this is not just theory. It may sound a bit abstract, but what I showed to you, but there is a real example for it. And we have it in the Volkswagen DPP, so the digital production platform of Volkswagen. So this is not only providing AWS services and a landing zone and a team helping you with all the deployments and the network configurations, but there are also reusable services on top. So we have this shared technical services layer where we have standardized solutions for the plant and station connectivity. And we also have the so-called DPP Quick Starter Kit. So this contains, on the one hand, automated way for you to get an AWS account if you want to very quickly start with developing prototypes or anything in AWS. But it also contains a catalog of reusable business solutions. And this is a description of the architecture of those microservice bundles. It is tagged with the used services, with the purpose of those services. And this is then helping all the DPP projects that we have to see here, there. Maybe this is something that's interesting for me that I could reuse. And this really happened. So for example, our parameter service. Initially, it was developed to support the calibration of rear axles and headlights. But it was then also reused for other purposes. So it was deployed for battery check stations, for battery manufacturing, because the use cases that you have, parameters that need to be sent to a station or configurations, this happens quite a lot. And so this is a candidate also for this DPP Quick Starter Kit. Next challenge, adaptability. And here we'll have a look at design principle, which we call elastic data models. First, why do we need to be highly adaptable? Well, usually if you are creating a smart manufacturing application, you are in a brownfield scenario. It could be that you create a new plant from scratch, but this is not happening so often. Usually you have your shop floor with all the devices and everything, and you need to support different protocols, UDP, MQTT, OPC UA in our example. And you also have a lot of the time changes of your production line. And this is a challenge because your applications need to be very robust and stable, and typically you say never change a running system, but you have this constant shake that there are changes, there need to be changes because of new requirements, and therefore your system needs to adapt quickly to those changes, or needs to be adaptable, and needs to be also agile. If you have disturbances, if you have missing parts, if you have lockdowns, then, or if you have any errors, then you need to have a quick reaction and be able to adapt to this situation with minimal impact on your business. Also here an example. So from our parameter service, this is the UI, and we have just a new field here, and for one setting that we have an additional attribute that should be integrated. So it sounds very simple. Change of your database schema, add it in the UI as a field. Not much difficult. But yeah, the business department said, we need to version the data model because the old data needs to be historized due to legal requirements, and it doesn't need, not allowed that it is changed. And also, we do not want to have a development team. We want to do it on our own. We are IT guys. This should be so easy because this parameter change happens quite often, that settings are changed, that there are new attributes. We want to do it on our own, not have a development team that does it for us. And we want to do it also during system runtime without any downtimes because we have 24/7 availability. So it should be done without a software change. So it is easy thing, could be a bit challenging. And here comes the idea of elastic data models. And you may be familiar with the term elasticity from EC2, so Elastic Compute Cloud, for example, ECS. And the idea here is a bit the same. Your data model should also be able to shrink or to expand if you need it. And we define it here as an elastic data model is an adaptable data model for structured data that can be modified during the runtime of an application without change to a database schema or business logic, like, for example, validations. And I'll give you an example how to implement this idea of an elastic data model and how we solve this challenge of this having a change during runtime of the UI without a database schema change. Well, the easy solution here is you store all your data in JSON objects. And as step one, you define a schema for those JSON objects. So in this schema, you could also include metadata like minimum values, maximum values, default values. And this could be used always then to validate those objects. And you can also then propagate this JSON schema to other microservices that are also then, it's possible for them to validate the data they get. Step two is then to take the schema and generate a layout schema or layout JSON out of it. Why? We are using an Angular library. It's called formerly dev. And this library takes the JSON layout and generates dynamically on the fly a UI out of it. So it is a template language, more or less, and it looks very much like the schema, the JSON schema. So this code generator took us only a few days to develop it. So this is very straightforward. And the benefit you have is, if you have generated this layout JSON, you have dynamically changed your UI without doing any Angular JavaScript programming. Formally is taking this layout, and it is also then possible to embed this layout in your dialogues, in your applications. So it doesn't mean that you have to do everything in your application only with Formally. It could be those areas where you really need these elastic data models. And Formally also then automatically implements for you all the validations that you need on minimum, maximum values, for example. And you just have to add also the labels in IATN config file, and then you are done. So all in all, we have 3 files. We have the JSON schema file, we have the layout JSON file, and the config file. And if you put metadata on the labels in your schema file, which is possible with some comments, then you have just one file that you need to change, one config file. And this helps you then to deploy it during your runtime. So you have a very highly configurable UI in this way. And it also supports data model versioning, because if you change your schema, you could keep the old schema with the old JSON objects. And it also works very well with NoSQL databases like Amazon DynamoDB. The cons is you still need testing. So it could be deployed during runtime, of course, but it's always good to have testing before it goes live. And if you keep your data in JSON objects, you're limited like in DynamoDB. So you do not have really an RDS system with a relational database. So if you need queries in this kind of style, then you are a bit limited. But if you look at DynamoDB, the limitations are not so big. So by using good indexes, you could overcome this. And there could be maybe also other application areas of this idea of the elastic data model. So maybe you can think a minute about it. Where do I have also this requirement that I need to change my data model? Could be here for station parameters, but it could be also for sensor data, for logistic tracing records, and maybe for many others. The third requirement, self-optimizing. And here I'll introduce the principle of closed feedback loops. But first, why self-optimization? So manufacturers are continuously optimizing their production workflows. They are working on optimizing cost, quality, delivery time, everything. But what we saw in the last couple of years, this is maybe not enough. So there are still disturbances, there are unforeseen things, and you have to react. You have to manage this. And the question is, how can you manage? How can you be prepared for the things you do not know? And from my point of view, one key benefit or one key element of this is that your system is able to heal itself, to optimize itself, so that you do not need to have people, humans, to check and to act, but the application can act on itself and can optimize itself. And from my point of view, this will be key to improve the competitiveness of manufacturing companies now and also in future. And how could you achieve this? Also a theoretic thing here. The principle of closed feedback loops. Some of you may know it from physical or mechanical systems. So also here the example with we have the rear axle setting value. This is the current value. This is then given to the controller. The controller updates the station with the setting offsets. Then the assembly process happens for the rear axle, so the calibration of the rear axle. And in the end, you have a final inspection of the rear axle. So this is typically not happening directly after the assembly process, but later, because if you produce a car, the car takes up weight during the production, and this could change the rear axle calibration. So the final inspection is done at the very end. And this result of this inspection could then be given as a feedback to the calculation of the new setting values of offsets that could also be station specific. And you can see here, this is then a circle, a closed feedback loop that optimizes the values. And if you look at our parameter service, we applied this principle. Again, the foundation here is you should have event-driven architecture as a foundation for those closed feedback loops. Because to utilize the results from this final inspection, you need some kind of communication channel. And this could be easily done with event channels with AWS serverless services like SNS, SQS, EventBridge. I've mentioned it. And there to use the publish subscribe pattern. So this final inspection result machine does not need to know who are the receivers of this information. By applying the event-driven pattern here with publish and subscribe, this information about this final inspection could be then read by our parameter service. And here we have it also as example in the architecture. So this end-of-line check is a component or a service that could run in different network, but it publishes the result event on the bus. And in the parameter service application, we have a parameter AI wizard component that reads it, calculates the new offsets, and sends those new offsets to the parameter store, which then sends it to the station. And the experience is that this really can happen automatically. So there, of course, is a manual check implemented, and somebody could review the values before they get sent to the station, so to avoid any problems. But the experience showed that most of the time, those automatically created offset values are trusted. And this is optimizing the whole production workflow. So last but not least, 2 short development principles that we also found for serverless projects. And one is testing. How should you test serverless projects? And here again, example of our parameter service. This was the user story, send a parameter to a station. So we have a user that clicks on the composite UI. This is then propagated or creating a send event, which is then sent to the left side here to the station. And we implemented all the Lambda functions, created unit tests with a very high coverage, also tackling all edge cases and error cases and everything. And what happened when we deployed it on our test environment? It broke because there was wrong IAM policy, there were misconfigured source mappings, subscription rule was missing. So a lot of problems that were not in the real source code and not in the business logic code. And this we solved then by implementing end-to-end tests. So here, just as an example, we used Postman. So Postman is a scripting or testing framework that you can use to test REST services. And Postman send it a test call to the composite UI or also to the parameter offsets REST API. And we implemented a station simulator application that also provided a REST API to get the value that the station has received. And by comparing both, it is then possible to check end-to-end if the use case has worked. And the principle here is that for serverless projects, end-to-end tests are more important than unit tests. So you may know this typical testing pyramid that you have a lot of unit tests and integration tests and few end-to-end tests. And here, from our experience, it is different. So there are more reasons that code can break that is not within your code, but within your configuration in security or in resource policies. And it's also more difficult in serverless development for your developers that they can check it locally. So this is better that developers can do the testing quickly by deploying. And you safeguard your components then in this way that you have end-to-end tests that verify that not only the single change worked, but the whole application is still working. And therefore, our recommendation is for smart serverless applications, you should have automated end-to-end tests running in the cloud environment. And second development principle, infrastructure as code development should be the same as your source code development. It means you should apply the same process, the same tools, if possible, the same development lifecycle with reviews, testing, also the same quality assurance and principles with modularization that you do for your normal source code that you have developed maybe in the past. And our recommendation here is that you give your developers same experience with infrastructure as code as they have it for their normal source code. And this could be done by not using CloudFormation directly. CloudFormation is a bit cumbersome if you have to develop with it, but to use tools like AWS CDK that provides a programming-like development experience that developers can use their preferred language to define the infrastructure and all those rules and resource policies there. And then to be as strict and rigid in the quality assurance and in all those processes as you would be for your normal source code. Apply the same principles there with testing, with code reviews, cleanliness, already mentioned. So, summary. What is smart serverless for smart manufacturing? In the beginning, we had challenges like 24/7, resilience, scalability, security. And we saw that serverless is a good architectural answer for this kind of challenges. Then we looked at additional challenges like reusability, agility, and adaptability, and this self-optimization. And came to the principles and patterns to use component-oriented design and homogeneity to allow reusability and maintainability of the application, to provide service stores that you can also provide those reusable services to other projects, other parts of your company, that you could leverage the idea of elasticity also for data models to achieve high adaptability, for example, for your UI. That event-driven architecture is, I would say, a must for serverless architectures. If it makes sense in any way, use event-driven architecture in smart manufacturing. And to really leverage self-optimization, apply the principle of closed feedback loops for self-optimizing systems. And, as mentioned, cover everything with end-to-end tests. Not only rely on your unit tests, have end-to-end tests for your whole application. And for the infrastructure as code development, do it in the same way as you do your normal source code development. Have the same developers do it, no separate teams that work on the infrastructure. Everything should be done in your same code base. So, these were the principles and patterns. I hope it was interesting or maybe inspiring for you. And this was my presentation. Thank you for your time again. I wish you a great further conference, a great evening today. And if there are questions, I'll be here. Happy to welcome you.